Hello there. My name is Caleb DeRocha, and in this presentation, I'll be talking about my research on candidate exoplanets. So first off, I'd like to show off our beautiful observatory here at BSU. This is located in the science building on the 5th floor, and here in this dome is where we do all of our astrophysical research, or at least the observation parts, I should say. And here's the image of inside the dome with the telescope and having the shutter open. In this picture, we are setting up to take calibration images for our data. So another name for an exoplanet is essentially extrasolar planet. That's the longer name for exoplanet. Essentially, that means that they are planets that are orbiting other stars. So this is a star system, another star system, and so on and so forth. That's essentially what exoplanets are. They are just planets in other star systems. So what are the ways that we can detect exoplanets? So we have radio velocity, microlensing, which is pretty new but rare, direct imaging, and the transit method. So radio velocity, that's simply using a Doppler shift effect to see the sort of circular motion that this star is making due to the fact that there's a planet orbiting it. So when a planet orbits a star, if it's massive enough, it makes the star wobble, and we can see that wobble happen with these absorption lines going back and forth on the spectrograph, because in some cases the star is moving away from us, and in other cases it is moving towards us. So microlensing is a new but rare way of detecting exoplanets. Essentially, it's gravitational lensing. As you can see here, this planet's causing the light to bend, the light from its star to bend, and it looks from the observer as if they are two stars. Essentially, just like how a lens, as you can see on my screen, sort of like makes my face sort of like distorted. Essentially, gravity can do that in the same way if there's a massive enough object sort of bending the fabric of space-time around it. That it's not common to use this method, but it is still done nonetheless. So, direct imaging, it is exactly what it sounds like. You just take a picture and you're like, oh, there it is. Yeah, so you have the star in the middle, planet B, C, and D. For some reason, the first planet's always named B, the first one discovered, I should say. That I don't know why that's standard, it just is. But yeah, that's direct imaging. Last but certainly not least, we have the transit method. And basically, this planet goes in front of the star, creates a mini eclipse, and then that mini eclipse basically makes the brightness of the star go down, which will be shown in the GIF in the next slide. So yeah, as you can see here in this little GIF, there is a star, and then there's the planet going around it. And when the planet is covering our view of the star, the apparent brightness of said star does a little curvy dance thingy. Also, as you can see in the GIF, this planet's very close to its star. However, even though this is sort of an exaggeration, and so for presentation purposes, there are planets that are more massive than Jupiter and are closer in their orbits to their star than Mercury is to our own sun. So yeah, it does get crazy with exoplanets. So what exactly is a candidate exoplanet, and why isn't it confirmed yet? So you see here in the transit, this is a simulated transit. Essentially, there's a U-shaped curve right here. As for this, however, these look like transits, but they have different depths. You'd expect that for an exoplanet, a transiting exoplanet, that you'd have roughly the same depth because unless the planet's changing size or if like there's another planet in the system, you'd think that there would be some sort of consistency here. Here's the thing. This is not an exoplanet. This is actually a binary star system. So basically two stars orbiting each other creates this sort of light graph. So, yeah, it is kind of difficult to figure out whether it is a binary star system or an exoplanet, so that's why it's kind of difficult to confirm. Plus, also with confirmed exoplanets, you do need the spectra of the um, atmosphere for that planet. Also, one thing to notice: this is a U-shaped curve. This is a V-shaped curve. Almost all the time, you see binary star systems have a V-shaped curve. However, V-shaped curves can happen with exoplanets. However, it is more often than not a U-shaped curve. Now, how do I find my transits? Well, it's simple. I go to the NASA Exoplanet Archive, which is through Caltech, and I just click what I need for my project, particularly Canada exoplanets. I put in the location for Bridgewater, and then I put in the dates that I want, and then I just press predict event, and then it brings me to all this stuff. So yeah, basically it brings me to this list of exoplanets that are visible within the time span and within our location that I input. And so I look through the period. I believe the period's right here. If it's a short period, I typically choose that because that means that the transits are going to happen more often throughout the semester. And so it gives me more opportunities to be able to collect the data. Also, I like to look at the transit duration. So it's roughly 2 hours long. So that's good. I want it to be kind of a long transit. Transit depth, it's pretty good. I like that. So, it looks good. So I'm like, yeah, this is good. This is me when I find the perfect exoplanet transit for my project. But then I realized that I have to stay up until 5 in the morning to collect this data according to this chart. So, yeah, this is the face that I made when I realized that. Um, just to say, I did make this meme shortly after doing this, like finding this, because it was I couldn't find any other exoplanet that would be good enough for my data, and honestly, it was worth it at the end. But yeah, I made this meme shortly after because I knew that it was exactly the facial expressions that I made, so I thought I'd make fun of myself for that. So how can we view these transits? Funny you should ask. There's this sort of thing called photometry. Essentially, you methodically choose a bunch of stars, and you just let each the star be analyzed for multiple pictures, and over time you just look at the brightness of it. So yeah, all these targets are basically there's the object aperture, which basically takes the brightness of the pixels of the object and analyze it, and then it compares it to the outer annulus, the pixels in the background. This inner annulus, however, is just a gap. It's mostly there just so that in case there's some sort of bleeding of light or pixels from the star into here, that the outer annulus, the actual stuff here, is not being affected at all. Otherwise, it would affect our data. So as for what each one does, the one that says object 1 right here, that is our target. That is the star which has the exoplanet. The reference star is usually it's a known star that can be used as a reference. It has a known magnitude that is stable. So we usually choose that. This one in particular does not actually have one, but it was just for purposes of presentation. And then we use check stars to make sure that this reference star is in fact stable in its brightness. We use 3 check stars to be very sure about it. And that way we are able to see if the object is actually transiting or not. So from that, we're able to get this transit. Now this is just a simulated transit. However, it is pretty much how it would look like, this U-shaped graph here. and then a steady brightness otherwise. And yeah, this is essentially what we get, and we can determine if there is an exoplanet there or not from this graph. So here at BSU, we use this software called MaximDL for data analysis, particularly for astronomy, since it is an astronomy software. This is what it looks like when you open up the software, and this is what the software looks like as advertised on basically websites. So typically with MaximDL, you're able to do photometry pretty well and get these nice transits. It's pretty good, but however, this semester it did not work. So yeah, it wasn't producing a graph at all in the software, and when we exported the data into Excel, it was pumping out weird numbers. So yeah, we had to kind of make a little detour and figure out other softwares to use. So I ended up using VPhoto, which is part of the AAVSO.org website. Basically, it is sort of an online software where you import your data and you can do photometry. However, in order to do photometry in VPhoto, I had to do plate solving. Essentially, plate solving is you have a certain patch of the sky that you're looking at. You're not sure exactly where you're looking at, but you know roughly where you are. So you put in the RAINDEC, which is basically the space version of longitude and latitude. And with the right ascension and declination, you can sort of have the software figure out exactly where the center of your image is. So say you put in such RA and such dec, you will have the software basically spiral out and look at all these connecting the stars, whatever, and basically compare, contrast stuff from its database and basically say, okay, I figured out that you are here. I had to do this 400 times because there was 400 images for one transiting exoplanet. So I had to use Notepad on my computer, well, on the computer at the observatory, and do a copy and paste of the RAINDEC for every single image. Needless to say, my hands were hurting after that. So after doing the plate solving, my next step was to go to VPhoto and import the images and let it do its magic with photometry. So essentially what I did was I clicked my target star and named it as targets. I picked my comparison stars and named it as comps. And then I picked my check stars and named them as checks. Also, comparison stars are the same as reference stars. It's just different name, same thing. The thing with ensemble photometry, however, that's different. With regular photometry, you just use one star as a reference. But since there aren't really any stars that you can use as a reference, because all of them have variable brightnesses, as far as we're aware, or at least we aren't sure if there are stars that are consistent in their brightness or not. So we just say, okay, these three stars, let's average them together, and basically make one virtual star, one sort of fake star to use as our reference star. So that is what ensemble photometry does. The check stars are to check the average of these stars, which is the virtual star, and then we can use that to compare to the target for our transit. So again, 2020 strikes, and yet another obstacle had come our way. So as I was making this presentation, I was like, okay, I should probably get some more graphs, like more data from the VPhoto. However, there was a software update with VPhoto, And as a result, I was not able to get the transit for like an earlier transit that I had collected. So yeah, that wasn't fun. And then I looked in the forum for VFOTs, and one of the software guys was like, "Hey, you can work around this by using the V filter. The V filter is essentially another name for the visible filter, which is basically just the green filter. I don't know why we use the word visible, but that's just common lingo in astronomy. So I changed it to the V filter, and still nothing. Yeah, that's again typical, but I had some workarounds. I did take a picture on my phone of the graph that I wanted, but unfortunately, that's what we're going to have to work with for now. But typically, I wouldn't be doing that, but of course, um, sort of have to work my way around things. So yeah, this was sort of the thing that I kind of wanted to download, but we'll work with what we have. So yeah, here's what I think is transit for Epic 2104 or 1157.01. But as you can see, I had the draw lines feature checked, by the way, which is why you see all these squiggles, which was what you don't want. Anyway, I digress. But yeah, you basically just it's just a complete mess. This whole gap here, and the focus was completely off the entire night. The clouds weren't any help. It was not a fun night. But even so, I do think this could be a transit. However, it's kind of like difficult to really confirm or deny it because there's not enough data points. But even so, there is sort of something that I found interesting about this graph, which I will mention in a later slide. But for the most part, you typically don't want something like this when you're doing exoplanet research. This one, however, my last night that I was in the observatory, this is the same exoplanet, but on a much clearer night. As you see, there's sort of a bit of deviation here and here, but I'll explain that later. But this depth, this exoplanet transit, is very much acceptable, and it is beautiful. This is why we want ensemble photometry, because it clears things up like this. As for this gap here, this is something called the meridian flip. Okay, so the meridian. Essentially, you have the celestial sphere right here, person in the middle. So you have north, east, south, west, zenith, and nadir. Zenith is basically anywhere on Earth you look directly above, that's zenith. Anywhere on Earth you look directly below at your feet, that is nadir. So if you were to draw a line, or an arc I should say, from Polaris to zenith to the southern part of the horizon, you would have the line that is the meridian. Essentially, the reason why that's important is you see this telescope. At this point, it is doing a 360 and going back. This is because of the gears inside the telescope. If we're to keep going, it would stall, and it would not be good at all for the machine. So essentially, if you look at this, you see your target rising. I'm using my my pointer here. As it gets to the meridian, this telescope has to do 360 around to sort of loosen up the gears. And then as the target gets over here, you can start observing again until it gets to a certain point past like towards the horizon. So let's look at our very, very nice transit for first off. So right here, this line, this black line, sort of represents the average magnitude for the brightness of the star, um, at least from what we observed for that night. And this black line right here represents the average for the bottom of the transit when it comes to all these data points. So we would typically say that the transit depth is around this, like 0.035, I'd say. However, the very bottom right here, there's a reason why I have it in a different color and a reason why that I am showing this. If you were to go from this part here to here, it's roughly a difference of a magnitude of 0.04 in brightness. Magnitude is another name for brightness, by the way, if I did not already mention that. So the reason why I point that out is that is also the overall depth of this transit, which is the same exoplanet. That is to say, obviously, assuming that this is a transit. More likely than not, it is a transit, but again, with the way the data is, it's really, really hard to tell. But anyway, typically you want to go for the average for the bottom of the transit, and my mentor and I sort of determined that this was the bottom according to how it's usually determined. However, if you were to do the overall depth, it is also 0.04 magnitude in a difference. So that being said, as you may remember earlier, I said that binary star systems have different depths in their sort of transits. Basically, that sort of like solidifies, if this is correct in my assumption, that it solidifies the fact that it is in fact an exoplanet. However, since the data is not really that desirable, we do have to get another transit of this exoplanet in order to completely confirm that it is in fact an exoplanet according to this. It's also slightly unlikely, but still possible, that it could be a binary star system that has two stars of the same size. It's not unheard of, but it's definitely not likely. But more likely than not, it is an exoplanet from the way that this looks and the way that the graph before it looks. So yes, this is a good graph, but as I mentioned before, there's a bit of deviation here and here. That is not just to do with the focus, but also to do with the fact that the object of interest, the star that we were looking at, was closer to the horizon at these points, so the brightness does change more drastically at these points. Also to mention that there was a bit of cloudiness here. There was a bit of a stalling of the mount here, where there was like a 15-minute period that I had to sort of fix that, which was actually very lucky, because otherwise I would have missed the bottom of the transit. Honestly, I'm surprised that I was able to get it done that quickly. And then there is the meridian flip being exactly where the shoulder of the exoplanet is. Because typically with the shoulder of the exoplanet, you're able to tell the size of the exoplanet. However, we were not able to do that, unfortunately. Also, there's some sort of like mathematical way to sort of make this curving of the star brightness kind of be in a straight line and see the transits for the actual shape that it is. However, that is not something we were planned on doing this semester, so basically this is fine the way it is for that aspect of things, but obviously we do want to get another transit of this exoplanet. So what's next? Well, I guess you could say wait for a VPhoto to start working again, and then collect the data, and then upload the data to the exoplanet archives or database. And then later on, probably obtain more transit data for EPIC 2104.01157.01. Gained the ability to view spectra of a star during an exoplanet transit. And lastly, to use MATLAB, which we recently obtained in the department, to analyze the light curves and determine the transit depth, exoplanet size, and star size. So I'd like to give a thanks to my mentor, Professor Jamie Curran, for guiding me through this project. I'd also like to extend a thanks to Dr. Kling and Dr. Arndt for working hard to get me to be able to have access to the dome after Thanksgiving, even though the university was making so that all labs, including the observatory, were closed to all students after Thanksgiving. Unfortunately, I was quarantined, and I'm actually currently in quarantine right now as of this recording, because my roommate tested positive for COVID. And yeah, I was not able to be able to work in the observatory after Thanksgiving anyway. Regardless, the efforts are much appreciated, and just thank you very much for your hard work in getting me to be able to do that if I wasn't in quarantine. Also, lastly, I would like to thank the Bridgewater Experimental Astrophysical Research Team, also known as the BEAR team, for helping me with the data collecting portion of my project. And thank you for watching my presentation on candidate exoplanets. If you have any questions or comments at all, please feel free to contact me at c1derosha@student.bridgew.edu, and I'll answer any questions or comments that come my way. Of course, keep in mind that I am going to be busy with schoolwork for the next few weeks, but for the most part, I will try to answer any and all questions in due time. Thank you, and well, stay curious.